Hey everybody, welcome back. I've got something I want to show you. This is a UDRC from Northwest Digital Radio. This is a Raspberry Pi. We'll put the two together and we've got a smart digital controller for a digital amateur radio station. I put it in a plastic case like this, hook it up to my radio, add a keyboard and a monitor, and I've got a digital station on the air. The key to making all this work is some software called Direwolf, and John Langner, the author of Direwolf, spoke at the 2018 MicroHAMS conference. Watch his presentation here.
All right, go ahead and get started. And our next speaker here is John Langner, WB2OSZ, got his ham license in high school. His interests include specialty communications modes such as RIDI, packet radio, SSTV, and APRS. John also loves to tinker. John has been published in Byte, 73, Ham Radio, and QST. John also developed software and had jobs in information technology. He will be talking about his Direwolf software that he developed and why you should never use a hardware TNC again, right? Please welcome John.
Okay, thanks, Scott.
We need to get
it's
you
an
up
honor
here.
to be here. Okay, so before we talk about getting rid of the TNC, I want to back up a little bit and first do a little bit of terminology and concepts. First, what is a TNC? Then we'll talk about getting rid of it. I'd like to talk a little bit about the challenges in building a demodulator. That was the most interesting part. APRS-TT. And if we have time left over, I'll talk a little bit about the improvements in the AX.25 protocol version 2.2 that makes it better for moving large amounts of information. First, a little poll. How many people are familiar with traditional packet radio or APRS? It's pretty much, like 90%. How many people are already familiar with the Direwolf software? Maybe half? No, less than half. Maybe 40%. Okay. And how many people know about APRS-TT? 3. Okay. Good. So there will be some new material here for just about everyone. So back when I got started in ham radio, this is how we sent text. Okay? This is actually a picture from my ham radio club in high school. And these teletype machines were developed in the 1930s. And as soon as they became available in the surplus market, hams put them on the radio. And radio plus teletype is RIDI. It was pretty easy to get started. You just built up a simple modem called a terminal unit, fed it into your transmitter, and off you go. But it wasn't very satisfactory. You'd flip on your transmitter, it would be sitting there 100% duty cycle, doing nothing, and you'd press a key, and it would just send out, one key or one character at a time. There's no error checking. Not very effective. So around 1978, some hams in Vancouver came up with a radical new way of sending data over ham radio. They called it packet radio because the information was sent in small packets or packages. Each transmission begins with a certain pattern called a flag that cannot occur within the data. You then have some addresses, like the station it came from, where it's going to, possibly repeaters. There's control information that tells the type of packet, the information part, the actual useful data. And then there's the frame check sequence, which uses a cyclic redundancy check. And the idea here is that all the earlier bits are put through a mathematical process with shifting and exclusive ORing, and it comes up with a 16-bit number. And if the data gets corrupted, that number will not match up. Okay, it's computed at the transmit end, recomputed at the receive end, and that 16-bit number should match. If it doesn't, something got corrupted and we just throw it away. So the way this was implemented is they had to put some brains in front of the modem. Okay, that's a brain there from the PowerPoint clip art collection. And so adding a microprocessor in front of the modem was then known as a terminal node controller, or TNC. And the original usage back then is people would have dumb terminals. They would talk to the TNC. You could compose an entire line of information, hit enter, and then it would get blasted out as a short packet, rather than tying up the channel for a long time. There are many advantages to this. Instead of turning the transmitter on and letting it sit there, it just sends out a short burst, gets out of the way. Each transmission has addresses of where it's coming from, where it's going to. This allows many people to share the same channel. There's error detection, so you know if the data got there properly. The higher level protocol allowed the TNC to gather up many lines of data, send them, do retries, acknowledgments, and get the information there successfully, or report that it didn't get there. And it was also transparent in that you could send any arbitrary data, not just text. You could send, say, a JPEG picture file. The Vancouver approach got things going, but they only from what I've read, they only made bare boards available. So that was not very convenient. People had to gather up all the parts, and it was a lot of work. And a few years later, the Tucson Amateur Packet Radio produced a complete kit. Here's the Tapper TNC-1. So the kit came with everything except the case. It was about $350, and this made it a lot easier for people to get started. But they throw an enormous amount of hardware at it. There's like 27 chips in there. There's an HDC controller that was something like $30 or $40, and that could have been done very easily in software. So to make a long story short, they came out with a newer model a few years later. Other manufacturers came up with products, and packet radio was pretty hot for a little while. So the TNC was designed with a dumb terminal in mind. Don't pay attention to the specifics here, but the main point is when you send information to the TNC, you might be sending it commands or you might be sending it data for it to be transmitted, and that depends on the current state. Or when information comes back from the TNC, it could be just monitoring of what's going on in the channel. It could be communication from a specific station that you're connected to. Could be changes in status, could be responses to commands. So it's not a real good interface for a computer, like if you were doing a bulletin board system or something like that. So this led to the KISS interface, right? What does KISS stand for? All right, simple. It was very simple. Now the personal computer builds up the packet to be transmitted, sends it to the TNC, and all that the TNC does is it puts it into an HDLC frame. Right, so here on the left, we have all the addresses, data, and everything. Send it to the TNC over an RS-232 line, and it just adds the flags and the frame check sequence. So that's all pretty simple. And this also opens a new market in that you can make a much cheaper TNC with much simpler software and less memory because it doesn't have to do much. So packet radio thrived for a little while, and then like in the later 90s, it kind of faded out, probably because the internet became available and we started using bulletin boards there rather than the radio. So along comes APRS, like late 1990s, and instead of connecting to one specific station, it's now more of a general broadcast. And while many people think of APRS as simply tracking cars moving around, or houses saying, I'm still here, I haven't moved, I'm still here, If you've listened to APRS, like 90% of it is, this house hasn't moved, this house hasn't moved. But you can do a lot more with it. There are a lot of weather stations A lot of people have home weather stations and transmit the data, so this can all be aggregated even if the internet is out. Telemetry can be used to send any sort of arbitrary data, and it has provisions for labels and units. You can direct messages to specific people or send bulletins to groups, and there's ways to send queries and get responses. So when APRS got started, we used the old TNCs from the 1980s. We now have these personal computers that have a lot more power, so why spend $200 on something from the 1980s and put it in the middle? You can just eliminate that, and the radio can go straight to the radio. It's cheaper, you can get better results, it's easier to make updates instead of just download new software instead of replacing ROMs. So that brings us to our main topic. What's Direwolf? This is software that can be used to replace the traditional TNC. It's open source, it's free, it's portable, it runs on Windows, runs on Linux, works on x86 or ARM processors, works on the Raspberry Pi. Oh yeah, even Macintosh. Without, I don't have one, but people in the community came up with the necessary adjustments and build procedures. It does work. Without adding any additional software, you can add a GPS receiver, it becomes a tracker. It can be a digital repeater, a gateway which talks to other gateways over the internet, well, not directly through servers and then to other gateways. And it can be used for APRS-TT, which 3 people knew about, and I'll get into that. And of course, it could be used as a virtual TNC for other applications that were written to use a hardware TNC. So where'd the name come from? I was just juggling different words around and accidentally fell upon this combination. And of course, direwolf is an actual extinct animal, so the name is used for other things, mostly in video games, so there shouldn't be any confusion there. Here we have an outline of all the different functionality. And we now have the outline on the right side, so as I go into each one of these little topics, you'll see how it fits into the big picture. Of course, the interface to the radios is audio. Okay, many different types of audio interfaces here. The original sound card, and we still use the term sound card even though they're not cards. The signal link USB. Okay, I'll back up a bit. So the audio is pretty straightforward, but the push to talk is always problematic. How do you tell the transmitter to turn on and off? In the early days, you'd use one of the status lines from an RS-232 port, but those are those are extinct now. The signal link USB has a Vox circuit, so it turns on the transmitter automatically when there's transmit audio present and drops the transmitter when it disappears. If we're using a single board computer like the Raspberry Pi, there's plenty of general purpose I/O pins available that we can use for push to talk. And here we have the UDRC, which is basically just a sound card. It was originally designed for digital voice, but it works fine in this application. And finally, lower left, this is a USB audio adapter. They run like $5 to $10. Just pop it into the USB port, and it has microphone input and headphone output. And you might notice this little wire here. I don't know how visible it is from back there. But I drilled a hole in the case, and it turns out that the most common chips have extra general purpose I/O lines available. Okay, so in some commercial products, they might be used for indicator lights or push buttons, volume up, down, whatever, but we can use that general purpose I/O for the push to talk signal. And there's actually 3 different commercial products already that use that technique. So that's a very tidy solution. You get your audio and push-to-talk through one USB connection. For software-defined radio, there's different ways we can get the information in there. Along the bottom, we have a 1200 baud modem, which is the most common. And I find it interesting to note that the APRS-TT standard that for packet radio says absolutely nothing about the modem. Okay, modem's not mentioned anywhere. But the Vancouver group started using the Bell 202 because they got their hands on a big pile of old modems for almost for free. And here we are 40 years later using the same thing. For 9600 baud, this is excitement back there. It's 4 times as fast. People were doing this in the late 1980s, so it's nothing new. Except back then, it was done with lots of hardware, and now we can just take the signal from the discriminator, put it in the computer, do it all in software. But the thing you have to watch out for is it requires a lot of bandwidth, about 5 kilohertz. So if you try using the microphone and speaker connections, it's not going to work. Okay, now we're getting into some other features that you wouldn't find in the hardware TNCs. Direwolf also has a touch tone decoder. So you can receive touch tones. It gets packaged up into a packet format that then gets passed up to the higher level here, to these other functions that process the received packets. So somebody could send a touch tone sequence, terminate it with a pound sign, and you could then write your own application that would process that and do something with it. In the opposite direction, all you need to do is, if you put DTMF in the destination address, instead of sending out an AX.25 packet, it'll send it out as touch tones. And it also has the ability to send speech. It doesn't have a built-in speech synthesizer, but if you put the letters speech in the destination, it runs a user-supplied script, and then that script can invoke a speech synthesizer. And it'll send Morse code. Okay, again, just put Morse in the destination, and it'll send it as Morse code. Okay, so we're talking about the lower half here, ways of communicating with the radio. And now we're in the upper half. These functions either process the received packets or create new packets to be transmitted. So beacons, of course, are things that you just transmit. If you get the location from a GPS receiver, you then have a tracker. It's all very flexible. Instead of sending fixed format information, beacons can also invoke a user-defined script. So that'll run, you produce whatever information you want, and then that gets transmitted. So that's useful for things like weather stations or telemetry. Direwolf also comes with what I call the telemetry toolkit. This is some documentation and scripts and sample code that allows you to measure quantities and then send information over the radio. And there's even an example in there of taking an analog to digital converter, hooking it up to a Raspberry Pi, measuring a voltage, and then transmitting it over the radio. But it's just a toolkit. It's not a turnkey solution. It's just a start for you to do your own custom application. There's also an APRS-TT gateway, and it uses the touch tone decoder down here somewhere. The information gets sent into the APRS-TT gateway. Direwolf also contains a digital repeater. Now, voice repeaters, analog voice repeaters, listen on one channel and then simultaneously transmit the same thing on a different frequency. But here, a digital repeater receives the complete packet, stores it in memory, looks at it, figures out what to do about it, and will generally retransmit on the same frequency. But Direwolf has the ability to talk to several radios at the same time, so it's possible to do, say, like crossband repeating between different channels. And there's all sorts of filtering in there, so you can restrict what gets repeated. Like if there's some annoying operator, you can say don't retransmit anything from the station. The internet gateway is used to connect disjoint radio networks. And I think many people are familiar with the case where the local iGate picks up something from the radio, sends it up to the servers, and then you look at it on APRS-TT or findyou.com. But it's really meant to be a two-way system. So say ham1 could send a message to his friend, anywhere in the world. It goes into the local iGate. It gets sent up to the APRS servers. The servers then say, well, where have we heard ham2 recently? And then the servers send the message to possibly several iGate stations near where ham2 has been heard recently. Then ham2 receives the message, and then the station automatically sends. Then that station automatically sends an acknowledgement, goes through one or more iGates off to the servers, and then the same thing. It says where was ham1 heard recently, and then the acknowledgement gets returned, so you know that the message was delivered. So many people set up receive-only iGates, but that's really like crippling the grand vision. That should be a two-way system to link. Again, the idea is to link together disjoint radio networks rather than just putting everything on the APRS.phi. Now, the hardware TNCs just had an RS-232 port, but now since we're using a computer, we have many other ways to talk to our applications. We have TCP/IP through Wi-Fi or Ethernet. We have Bluetooth. And we also have the advantage that we can talk to many different applications at the same time. So now I'd like to talk a little bit about the challenges of making a demodulator work with real-world signals. Here's a pretty good-looking APRS signal. On the left, we can see it's a lower tone. It shifts to a higher tone, shifts to a lower tone again. So it's called audio frequency shift keying, very simple, very primitive. So the challenge then becomes, which tone are we listening to? The higher tone or the lower tone? And one way of doing this, there are others, is you might have bandpass filters for the two frequencies, take the amplitude of each signal, do some low-pass filtering so the data can get through but not the original audio carrier, and then say which of these is stronger. So that works great on a perfect signal, like we just saw, where they're both the same amplitude. Yeah, there's different ways to implement this. Back in the old days, you might use inductors and capacitors. Later on, we'd use active filters. You can do the same thing in software. I have no academic or professional background in DSP, so it was a matter of a lot of reading, a lot of experimenting, trying different things, a lot of tweaking until it worked better. After a lot of experimenting, I got it to decode perfect signals, patted myself on the back, good job. And then I started listening to real stuff over the radio, and guess what? Didn't work so well. So then I discovered this TNC test CD that was constructed by WA8LMF. And what he did is he recorded a bunch of signals while driving around Los Angeles during rush hour. So it was total chaos, okay? Everybody piling on top of each other, all sorts of different devices. It was wonderful. And this is an important distinction right here, track 1 and track 2. On track 1, he took the signal straight from the discriminator of a receiver, so it was nice and flat, okay, different, well, flat audio, flat response, wide bandwidth. He then ran it through a low-pass filter to simulate the effect of the de-emphasis used in most receivers. Now, I'll be getting into that. And this has pretty much become the de facto standard. People don't talk about signal-to-noise ratio or bit error rates or any of that. If you want to evaluate TNC performance, you take this CD and you see how well your TNC does with it. So many people have tested many TNCs and software, and they've mentioned how many packets are decoded, and I've gathered them all together, and here are some of them. Columns don't line up. It must be a different version of PowerPoint that handles tabs differently. But anyhow, I've separated these. Well, first the disclaimer. This was done by different people, different times, different conditions. So don't take the numbers too seriously. Most people don't specify if they use track 1 or track 2. But when we put the numbers together, we do see a pattern here. The ones in yellow with the asterisk are the software implementations, and the ones in white are the hardware modem implementations. And when we plot this out, what we see are the hardware implementations usually get somewhere from the 700s to the upper 900s. And then along came the first generation of the software TNCs. They didn't do too well. Okay, one of them got 130. Another got about 500. Not so hot. So this gave the software TNC approach a bad reputation, and you'll find a whole lot of 10 and 15-year-old articles out there that say, for best results, you absolutely must buy a hardware TNC. Don't bother with the software approach. But then later implementations did a lot better, and they leave the hardware modems behind. You had a quick question?
You're referring to 1200 baud.
This is 1200 baud, yeah. So, well, there's a lot of outdated information out there. I'll just leave it at that. So what I observed is that results from track 1 were a lot better than results from track 2. And in Direwolf, we have the audio level here. So the first number is the overall level as it's coming in from the very beginning. And then these two other numbers are the strengths of the two tones. So you can see in one case, they're the same strength. In another case, one is twice as strong as the other. So the explanation for this is the 1200 tone is a certain amplitude, and the 2200 hertz tone is half the amplitude, and that could be explained by having the low-pass filter that's decreasing the higher tone. And this is the reason for it. The voice transceivers are not designed for data. On the transmit end, we have something called pre-emphasis, where it boosts the higher frequencies. And then on the receive end, we have de-emphasis, where there's a low-pass filter that decreases the amplitude of the higher frequencies. In theory, it should balance out, but a lot of the time, they don't. So we end up with different situations. So in this case, if you look at the audio waveform, you can see that the lower frequency is much larger amplitude. And you could explain that because the transmitting end probably used flat audio, so they probably went straight into the modulator rather than going in through the microphone input, which would have the pre-emphasis. And then on the receive end, we have the de-emphasis that decreases the high frequency amplitude. This is the opposite case. Opposite case, we have the preemphasis, the boosting of the higher frequency, but the receiver is flat audio, so you can see where the high frequency now has a larger amplitude, and it's kind of spiky. Now, this messes up the comparison. You know, you want to know which one of these tones is stronger, but the radio is messing it up. So, it's, you know, this one is twice as strong, or this one's twice as strong, and the decode rate goes down. So, in my first experiment, I tried adding automatic gain control in there to compensate for it. And it worked. It had some improvement, but it was not ideal. And the next thing I tried doing was adding fixed gain and having multiple decoders, multiple HDLC decoders after that. And what I found is that when we use the original implementations, or the original signals through one decoder, it worked very well on track 1, which is, remember, the flat audio. And then I tried boosting the higher frequency and used a different decoder, and that worked a lot better on track 2. So what do? Well, you can run 2 of these in parallel, which raises the question, well, what are the best numbers to use in there? So I did a little study, and these are the number of packets decoded from each of the tracks, trying different gains. And it's kind of spread out. So what I ended up doing is running 9 of these in parallel with all sorts of different gains. It kind of overkill. Maybe 3, 4, 5 would work just as better, but I just total overkill. Because the earlier part of the demodulator is computationally intensive, but when we get down here, it doesn't take much processing power, so there's not much expense to doing a bunch of these at the same time. And over here on the right side in yellow, you see these little bars and underscores. A vertical bar means a packet was decoded successfully, no errors, and the underscore means nothing. So we can see we're running 9 decoders here. And on one signal, one set of them does real well. On a different signal, another set of them does real well. Give you a moment to read the words. So another experiment I thought I'd try doing is how many of the packets there have single bit errors, and could we do something about this? So instead of processing all the bits as they come in, I rewrote the code so it would look for the start flag. It would gather up all the bits into a buffer. It would look for the end flag, and then we would go back and process it. Now, if the frame check sequence was not correct, I would then go through it and flip each one of the bits one at a time and recompute the frame check sequence and see and see if the frame check sequence was correct. Now, it's important that this is not forward error correction like others were talking about, okay? We're not sending extra information that you can go fix it up to how it should be. This is just, it's not right. What can I do to make it appear to be right? It came up with a lot of false positives. Now, there's about 65,000 different combinations for the frame check sequence. But when you try hundreds of different combinations of flipping the bits around, you're going to run into a lot of false positives. So I added a sanity check to it. A valid AX.25 frame is going to have first it's going to be a multiple of 8 bits. Forgot to mention that. Addresses are 7 bits each, so the complete address part is going to be a multiple of 7, did I say bits? Bytes. There's going to be between 2 and 10 addresses, 7 bytes each. And if we know that we're dealing with APRS, we know what the control and protocol bytes are going to be. And the information part is going to be all printable characters or a few other special characters that are used. So by running it through the sanity check, we're pretty confident that we have something that's valid. Not 100%, but pretty good. So now we have a new score, but I don't put this into the comparison tables because it's cheating. It's okay. We should only check, or we should only compare frames that are received correctly, no errors. But if you're using APRS, this will squeeze a few more out. Or maybe if you're using very weak signals from satellites, this could pay off. You don't want to use it if you're transferring important data. Now, I call this the forgotten part of APRS. This is not a new idea. This came about, I think it was now 2002, where the father of APRS came up with this idea and did a prototype where he took a touch-tone decoder chip and hooked it up to the parallel port of a computer. Okay, this is going way back. And he wrote some software that would then take the tones and then change them into APRS packets and retransmit those. And this is the justification. Not too many people have portable equipment that have a built-in TNC, but almost everyone has an old HT that can generate touch tones. So this allows everybody to participate and put information into the APRS network. So this is the general idea. You have 2 radios. The first radio picks up the touch tones. The gateway then takes those tone sequences, converts them to an APRS packet and transmits it on another channel, and then it sends an acknowledgement to the original channel. This could be in Morse code or voice, saying, okay, I received the signal. Now the tone sequences are composed of one or more, I call them fields, where the fields are different types of information. And there's a certain pattern here where you have a field of different tones of, A, B, C, D, or the digits. Use the asterisk to separate the fields, and at the very end, you hit the pound sign. Now, fields beginning with A are used for call signs or objects and other attributes. A field beginning with B is used for location information. And there's several different ways of representing locations. For example, you might have a list of 10 fixed locations, and that could be represented by 1 digit. So that would be useful. Say you had some kind of race. You have start, a couple checkpoints along the way, and finish. There's the ability to have different types of grids based on either latitude and longitude and latitude, or UTM. But you wouldn't specify coordinates like anywhere in the world. Rather, you would define a local region, and then you'd specify a smaller number of digits within that region. A field beginning with C can be used for general comments, or there are specific cases, like if there's a single digit, you use a predefined table of different status, like en route, arrived, off duty, whatever. And D is mentioned as being for messages, but there was no definition of how that would be used, so I haven't implemented it. Now, you notice none of the fields in the original specification began with a digit, so I added my own little extension where you could have all short, all numeric fields, and then you could define what they mean. So using the original specification, you have horrible stuff like this. Yeah, okay, horrible. So the example here is you might have a bicycle race and you wanted to say that bicycle number 123 is at location so-and-so, and we have an emergency situation. So horrible. No one's going to use this, okay? If you're out monitoring some event, you're not going to sit there and punch it in. That's ridiculous. So what I did is I came up with a way that you can define very short numeric-only sequences for special cases. Okay, it requires no coding. You just put it in the configuration file. So you might say a field of exactly 3 digits would mean the first digit is one of 10 locations predefined. And then the other 2 digits would be an object number. So the object could be staff for the event, vehicles, participants, whatever. And this all goes in the configuration file. So if you were at checkpoint number 5 and canoe number 12 came down the river, you could just punch in 5, 12 pound, you're done. I have a little more complete example here for a hypothetical search and rescue event. And the scenario is that a bunch of people are called together very quickly to search for somebody lost in a park. And APRS trackers are not available, but someone wants to watch everybody's movements on a map. So what we can do is we can define a message format where 1 digit represents the team, and then we have 6 digits for the X and Y coordinates within a predefined region. So here's an example. We have the UTM coordinates, and luckily it works out that we can represent the east coordinate with 5 digits and the north coordinate with 5 digits. So that's how people can specify the location. So if you read from your GPS, that UTM location, you can then just pull out the 3 digits for the X, 3 digits for the Y, and just send those. So if the third team wanted to report their location, they'd just say 3, the east coordinate, the north coordinate, #, and that's all you need. And then right here, it appears on the map. Or for more complicated situations, you can use multiple fields. We would use the same 7-digit numeric field for the team number and location. And we could add extra things like a single digit might represent a status. A C followed by 6 digits is the standard form for frequency. Oh, yeah, I forgot to mention, after they transmit that, the APRS-TT gateway responds in voice. So it might say team alpha at this location, subject found. So a few people have used this for some events, but I think it just needs a lot more publicity. I think it's a very powerful and useful concept. Just need a few more people to spread the word and give it a try. And so here we have Team A. In this particular application, if you click on the icon, it shows you the information like the frequency. And some applications, StarTrack in this particular case, will show you information in tabular format. Okay, so that's APRS-TT. We're a little tight on time, but I would like to very briefly mention a feature in AX.25 version 2.2 that makes it better for sending large amounts of information. First off, the original protocol restricted you to 256 bytes of information in a packet. Okay, after the addresses and everything, the actual useful data was restricted to 256 bytes. And in the later revision, there's no specific limit, and the two stations can negotiate. So one can say, I want to send 4K at a time, and the other sends back, no, I can only do 2K at a time. If you are acknowledging data, this is the stupid way of doing it, one at a time. So let's say the sending station sends 5 lines of data, right? The quick brown fox jumps. The TNC behind the scenes assigns sequence numbers. So it would send the first one, the receiving station says, okay, got it, ready for the next. You send one, okay, got it. Send another, okay, got it. This is very inefficient because each time you want to transmit something, you have to sit there, wait for the channel to be clear, wait a random amount of time so you don't step on to minimize the chances of stepping on other people. And then you have to usually turn on the transmitter, wait about 300 milliseconds, just sending filler information, because it takes a while for the transmitter to stabilize and all that. So there's a lot of overhead in switching back and forth between transmit, receive. So this is the better way of doing it, and this is known as the window size. It's the number of packets that you can send before waiting for a response. So here we have 6 lines to send with a window size of 3. We turn on the transmitter once, blast out 3 packets all in one transmission, then turn off the transmitter. And the receiving end then says, okay, I got 3 of them. The sender sends 3 more, and this is a lot more efficient. So with the 2.2 revision, you have the option of using 7 bits instead of 3 bits for the sequence, which means you can have a much, much, much larger window size. You can send lots of stuff in one transmission before you wait for an acknowledgement. The other big improvement is the way you ask for resends. In the original protocol was written back in the days when we measured memory in kilobytes, but we don't do that anymore. So in this example, suppose we send 5 lines, and then the second one there is crossed out, meaning it gets clobbered by some sort of radio interference. So using the old protocol, only packet or frame 0 was received successfully. The receiving end says, well, the receiving end discards everything it wasn't expected in order and says, go back and start transmitting from number 1. So this is very inefficient. Even though frames 2, 3, and 4 got through successfully, the receiving end is so stupid, it didn't remember them. It just dropped them on the floor and says, start resending from 1. In the newer protocol, there's something called selective reject, and there's now a new command which asks only for those that were missed. So in this example, we blast out 5 packets. Numbers 1 and 3 got lost due to interference, and now the receiving end remembers the others and just says resend 1 and 3, and it puts everything in the proper order. So it's much more efficient. Now, unfortunately, this came out in 1998 when connected mode packet was on the decline. So what you find is most of the implementations were done before that time, and they never went back and updated it with these new features. And there are some partial implementations of this. I think mine's fairly complete. But I think the point I'm making is if you're moving large amounts of information, you might want to look at using the 2.2 protocol. Oh, and finally, the compatibility between the two of them. There are two different commands for establishing connections. So if you start with the newer protocol trying to make a connection, it would send a connect request using SABME. The E stands for extended addressing. If you have an older implementation, it says, I don't understand what you're talking about, and it sends back frame reject. In that case, the sending station then says, oh, you don't understand the newer protocol. It sends SABM, which is the older protocol, and then the older station says, oh, okay, that's cool. So it's very nice. If the older protocol, or if the station originating the connection uses the older protocol, it just works the old way. But if the newer implementation tries to connect, it fails and falls back. And that's it. I'm only 3 minutes over. That's it. Yes, not done yet.
I'm curious if you've done any implementation or thought about implementing the fabled FX.25.
I've read about it, and it's a cool idea. What it does is it takes, you have the original, I'll just talk about it. You have the original AX.25 frame, and then it puts forward error correction around it, so that we are sending extra information, I think, before and after. So a suitably equipped station could use that to properly fix errors instead of, like I did, just flip the bits and see if it works. I've read about it, but no, I haven't made any progress there. But the nice thing about it is you still have the original signal in the middle, so existing stations just pick up that part, but the new stations, or the stations that understand the forward error correction, would use the whole thing. Is that a good explanation? Okay, I've read about it, but I haven't done anything in that direction.
And there were several things that you talked about that when there were several of us in this group that were running TCP/IP back in the day, and we would gut out our TNCs with KISS mode, and then the TCP/IP software would implement a lot of the protocol, and there was stuff in there that was way beyond us at the time, but now it's old hat. And does Direwolf do KISS?
Yeah,
Okay.
yeah, it implements KISS.
Thank you, sir. You mentioned the ability to support a 9600 BPS connection. There's some discussion around the possibility of some of us who are doing FSQ right now possibly adopting Direwolf and thereby getting additional modes open to us, including packet. And so my question is, a typical setup, Raspberry Pi, UDRC, FM radio with 6-pin interface, is that going to be capable of doing 9600 BPS?
Yes.
So it's not using an audio interface in that case, based on your comment?
Right. The big three radio manufacturers on some of the models have little 6-pin DIN connectors, and that has wideband audio suitable for 9600 baud.
So in the interest of getting people out of 1200 and into faster speeds, what's the best way to essentially, if you had, say, a UDRC equipped Pi type setup or any other Direwolf setup, to have it essentially decode, be able to talk at 1200, but also at one or two other speeds?
Okay. The software allows you to use a stereo sound card and you can use different speeds on the left and right channels. And for receiving, it's okay, but on transmit, it'll only do one at a time. It's not smart enough to merge them. But my recommendation would be, if you're running 2 radios, to use 2 completely separate sound cards. The reason is each of the incoming, well, the reason is if you use 2 different sound cards, the decoders can run in 2 different threads. Well, they do run in they'll run in 2 different threads, and that'll take advantage of the multi-core processors that we have available now.
Okay, I have a few things, John, over here.
Oh, John.
To the point of the multi-speed, there is an experimental page on the UDRC group on groups.io. I have actually run multiple modems in parallel on the same sound stream coming in and out of a radio, and made it work. Actually had 1200 and 9600 on the same channel and just did it on a packet-by-packet basis. So it's possible, it's dangerous, you're going to irritate people if you don't know what you're doing, but it is there and it is possible. John, could you comment on your new duplex that's in 1.5, both for satellite, and could it be put into a true repeater mode? And also, you might want to mention some of the higher speeds that you've implemented in the modems.
Okay, yeah, version 1.5 will work in full duplex. Previously, it would transmit only if nothing was coming in. But of course, you'd have to use 2 different radio channels for that. But full duplex is there now. As for other speeds, some people challenged me to implement phase shift keying, and I just did it on a whim, not knowing what I did, and it seems to work. But I don't claim that I know what I'm doing. But if there are any modem experts out there, if you want to create extra modems, send them along. We'll integrate them in there.
I think you want to catch him at lunch? You want to be the last guy that holds everybody up, or we're welcome to. Just there's anyway. All right. So one more question.
So you're one of the very few that has actually given any thought at all to 9600 baud in using sound card devices, and from the reports I've heard from my buddies who really have dived in, it's a good implementation. How much interest are you seeing in 9600 baud now that it's getting a lot saner because you don't have to have a 9600 baud TNC?
Yeah, not enough. I've heard back from some people that they're using it, but I really can't gauge how much it's being used. But again, the challenge is you need the wide bandwidth audio. You just can't use the microphone and speaker connections.
So that's obviously one of the motivations here, right, is to show everybody how easily we can do this. So thank you for coming, John.